Okay, so we're going to pick right up with where we left off yesterday. Today is our last class of the week. It's a short week with the holiday and all. So we're just going to do this one problem, and then we're going to break up into the groups, and you'll do the stuff on the board. So we looked yesterday at a 3D problem where we had three different forces where we knew the directions, but we didn't know the magnitudes of the forces, right? And so we put magnitudes were the variables of the forces, you know, FAD. This magnitude, and this magnitude. We had to solve for those three things. So we set up equations and we solved it that way. This one's a little bit different in that we have we only have one unknown force. That means set up the equations to solve. So it's a slightly different, but you noodle through it the same way. You know, you draw the free body diagram, you write the unknown force, and you know, forces and all that stuff. So here's how we are going to do this. And let's just use the free body diagram here. It's all pretty much set up for us. So we know that F1 equals what? What's the Cartesian form of F1? Yeah, or just 400J. That's kind of, you're doing the linear algebra notation. Yeah, it doesn't matter. 400J, we'll just use J, right? And what's the Cartesian form for F2? Minus 800K. Then there's F3, which we're going to have to go through that whole position vector to, you know, force vector kind of thing, right? So F3 is just going to be vector in Cartesian form is going to be its magnitude, which we know is given to us at 700, times the position vector divided by its own magnitude, position vector RB. And that's going to give us 700, right, times, and RB is, so what is the position vector RB? What's the x component of RB? -2i. The y component is -3j, do you see that? And the z component is 6k. And the magnitude of that is I think it's a nice number. Oops, 6 squared. Is it 7? Yeah, because that becomes 36 plus 9 plus 4. Yeah, it becomes 7. So so that means it's going to be this is essentially 7, which means it cancels out and that becomes 100. So it's basically going to be minus 200i minus 300j plus 600k. Okay, so now we have the forces. Our unknown force is just going to be, you know, so our unknown force F is going to just be Fxi plus Fyj plus Fzk. So the next step is to do what? Yeah, sum all the x components, make them add up to 0. Sum all the y components, make sure they add up to 0. And that's how you find x, fx, fy, and fz, right? So I think I can probably squeeze this in over here. So the sum of the fx equals 0 is going to give us what are all the x components in this system of forces. Yeah, we got the negative 200 for F3. And what else? Plus Fx, the magnitude of the x component of our unknown force. And that equals 0, so therefore Fx is going to have to equal 200 newtons. And the sum of the Fy equals 0 is going to equal, okay, all the Fy's. What do we got in terms of y's here? Yeah, you got 400, and you have F3 has a minus 300, and we have Fy there. Therefore, Fy equals, it's going to equal minus 100. And the sum of the Fz components means that we're going to have minus 800, that's F2, plus 600, that's F3, plus Fz, and therefore Fz is going to equal 200. So that just tells us then that our solution for F is going to be 200I minus 100J plus 200K. That's the force that we need to apply to that particle so that it remains motionless. So in many ways, at this point in statics, what we're sort of doing is like three-dimensional accounting, right? We're accounting to make sure everything is, correctly. We're accounting for all the forces, but a business accountant would sort of recognize this stuff, we're adding all the influxes and the outgoes and making sure that everything's accounted for, right? Well, we got to make sure all the forces are accounted for, and if there's any unknowns, we figure out what those are, right? But we have three dimensions to work with. Up to 3, right? So it's just kind of writing those equations and solving them. Okay, any questions? How's that feel? I think, well, there's another example, but this one is this on your handout? So this one is a little more complicated, but it's the same idea as the first one. It's just that in this one, all three forces, you have to start with the position vectors to find the Cartesian representation of each force. And we just don't know the magnitude of each force again. So it's kind of like the first problem where we had those, we knew the direction of all the vectors, but we didn't know the magnitudes of those forces. Again, we have the direction of all these vectors is well known. We just don't know what their magnitudes are. So rather than kind of going through all really long, I'd like to have, this is our last day. I'd like you to have some time at the board. What I think we'll do is we'll just draw the free body diagram and then sort of come up with the just the overall plan for this thing. And then we're not going to sort of grind it out. You can sort of work it out on your own, right? So the free body diagram of this one here, we can look at A, and the force pulling up at A, well, we know the plate has a mass of 150 kilograms, and that's going to be the same. So the force pulling up at A is going to have to be the same as the mass, the weight of that plate, right? Which is going to be 150 times G, right? Which is going to be 1472 newtons. And then we have these three forces, FB, FC, and FG. Oops, FC. and FP, right? And FB is going to be just the unknown magnitude times the unit vector, right, which is RAB divided by its magnitude. And the same thing for FC. And the same thing for FD, right? And we can work all those unit vectors out, but the point is these three unknowns are going to be scattered between all of those vectors, and we're going to basically end up getting three equations and three unknowns from that. Actually, why don't we just scribble this out? This could be useful, because what's interesting about this one is that the distribution of the forces, the unknowns, kind of gets, we sort of have to tip the matrix to make it a system of equations, right? So it's going to be FB times, and actually, let's just write it out. I'm going to do that linear algebra notation, but that could be confusing. So 4I minus 6J minus 12K, right? If you do all that position vector stuff, that's what you're going to get, right? And the second one's going to be FC times, minus 6I minus 4J minus 12K, right? And the third one's going to be FD times minus 4I plus 6J minus 12K. And then, that W vector is just going to equal 1472K. And so basically, we sort of have to add all of these vectors together, right? The sum of all these things has to equal 0, right? That 1472 is the weight of that plate, which is the same value as the tension in the cable that's keeping it from falling. It's only in the K direction, and it's acting upwards at A because that has to counterbalance the plate itself, right? Good question. Anytime I do anything weird like that, you have to ask me why I did that. Because it's weird to see the weight going up, isn't it? Gravity didn't change here. It's just that that's the magnitude of the force that has to support the plate to keep it from falling. So we then just write, the sum of the fx's has to equal 0, right? Well, that's going to have to be, 4fb minus 6fc minus 4fd, right? And you can do the same thing for fy and fz. And now you've got your three equations of three unknowns. You can figure out how to solve those because you're taking linear algebra. And that's basically it. Oh, there's one thing it looks like I left off. Nobody caught that, but that's because we're going too fast. Each one of these, those were the position vectors, but we have to divide them by the magnitude. And it just turns out that the length of all those cables happens to be 14 meters, which is pretty handy. So to make some unit vectors, you have to divide each one of those things by 14. And so this whole thing is going to be actually 4 over 14 FB minus 6 over 14 minus 4 over 14. And you could get rid of it, except that that 1472 would then sort of have to be multiplied by 14. If you want to multiply everything by 14 and make 1472 bigger, you can do that too. But anyway, that's the basic idea. Talked way too long. I mean, I could go all the way. Do you want me to finish this? How do you guys feel? You want to just dive in and do the problems? Problems, right? Good problems? Okay. All right, let's do it. Yeah, so why don't everyone start with problem 1.7. Just to knock out the 3D one, because I just want to make sure that's probably the more complicated one, and then do one of the 2D ones when you're finished. So what happens is when you get into some of these complicated systems of equations, you want to find an easy way to solve it. And one way you can do that is with Octave Online, which is a really nifty tool. You can just Google Octave Online, and it takes you to their site. You took the MATLAB class?
Yeah.
Yeah, so this is basically an online version of MATLAB. You can use it on any computer that's connected to the internet. And there's a few ways you can do it. I think, you know, we used to do like A equals something and then B equals something and then A backslash B to solve that. But you can also do row reduced echelon form. So you can actually do like your whole system. You can call it, I don't know. Basically, this is your equation of equilibrium, right? And what you do is you just list the coefficients of each. Can you see that far? So it's going to be 4/5. What do you got there? 4/5, -1. Sorry? No, I gotta go. Yeah, so cost. Abbreviations. Yeah, don't forget the J out there. Oh, yeah. Okay, what's the second one? No. Oh, you can wear it. 0 4/5, then what? And it's 12 25ths, and then 0. And then the third row. 3/5, 0, 4/5. Positive. Okay. And then this becomes our matrix, right? So you see this, and all we've done is we've put everything, all just the numbers in front of the coefficients in front of all those unknowns. So because we have them, you know, these are all the, you know, the x components of the unknowns. I mean, these are the coefficients of F1, X, F2, F3, and so on. And then all you can do is you just say RREF, which is row reduced echelon form of your variable equation of equilibrium. That'll give you those numbers. Now it looks like we have an error because that's not the right number. It's not the right answer. The answer should be 776, 466, and 879. So this is definitely a challenge because it's 3 by 3. A lot of ways you can mess up. And pause it. Let me pause this there. I think I pause anyway. Yeah, so we're paused. So we can go back and let's make sure we did this right. Actually, let me just take a photo.
Well, no, you've made as much progress as you can.
Kind of goes to show you how careful you have to be with this accounting stuff. Yeah, let's go back to your work here. That's better. All right, let's go here.
Side of 30 is 1. Two equations, two unknowns. So solve for one, either AB or AC, and then substitute it in there. Yes, either one. Or not multiplied by. So 4 multiplied by 5 over 4. Or root 3 over 8. Or 5 root 3 over 8.
The nice thing is you can just go back up here and fix it this way. So this becomes a 0, and this becomes 9/25. And now we can do the row reduced echelon form again, and we still have another mistake. So let's go back and look at the other ones.
Yeah, at this point, you basically need to. It's going to be friendly. 15 root 3 plus 1 over 40 times AB. Once you can deal with it, you can multiply that by that and divide by all this stuff. You can put all at once. It's just you can calculate what this is like 4 decimal places and be what it's yeah. That's what I would do. 15 times 40 divided by 15 through 3 plus 20 equals 478.46, which is correct. 478. So I'll set that. Yeah, I would stuff it back into this guy and solve for AC this time.
Yeah. That's all right. That's
Or actually, you already did solve for AC.
Yeah.
Yeah, so just subject to that one.
We know this in our AB.
Yeah, but you plug the AB into an AB.
Yeah.
Oh, yeah, right.
Yeah. If there's a farm problem later where we're working with EI, and O.
So rounded to. Yep. Correct. Hell yeah, dude. 518 times 2,000. Wait, is 2,000 kilograms or? I don't know what I don't remember what it is. A regular or imperial ton is 2,000 pounds. Yeah, it's 1 ton. It's like, yeah. I don't know. Or, I don't know. I don't work with tons. Oh, it's like fathoms. Well, fathoms are 12 feet.
Is it?
Or 6 feet.
Yeah, 6 feet.
Is that 6 feet or 12? Yeah, no, 6 feet. And it's 1.2 knots per mile. Yeah, yeah, it's nautical mile. 1.2.
Well, it's like an arm's length. Right?
Yeah.
Arm's length.
Yeah. Well, that was disappointing. What? Doesn't work. It's an LED. Or it might be the wrong direction.
Yeah, but you can't even think about it.
Yeah, that's what a diode is. It's one direction. I don't do electronics. Neither do I, but I know that much. Yeah, I just not know the voltage. Yeah, LED light anytime. Diodes are great because they only go one direction. So like you fucking plug your shit in. Why isn't it working? And then you realize that plugged in the red toward the wrong direction. There's a reason I don't want to be an electrical engineer.
Have you seen that stuff on graphene?
Graphene? Yeah, I know what it is. Yeah. It's super cool, but it's super expensive to make. So it's like, well,
Yeah, it's like
yeah, well, it's like prohibitively expensive to mass produce. Like to manufacture it took a long
is the would they take like
Is that how they're doing it?
yeah, and you pull off a layer and then you dissolve the tape. But I don't see how the end of it is back and
Well, it's, I mean, it's not all one moment. Is it?
that's how it works.
Is it just strands of it together? I don't know. I mean, it sounds cool, but it also sounds like kind of one of those like science woo things, like cold fusion, where it's like, oh yeah, this is gonna revolutionize that. It's like, well, like Philly was saying in the later past, like, you know, in 1960 they said we're about 20 years away from having fusion power. In the 1980s they said we're about 20 years away. In the 2000s they said we're about 20 years away. And recently, you know, 20 years later, they said, you know, we're almost there. So, all right, let's see how.
I think it's more like
Maybe. I mean, like if they get it to work, awesome. Like that would be amazing. But the thing is, I'm just always super skeptical about anything where people say like it's this super material or it's this product that's going to solve all of our problems. it's like, well, you know, most of the time, like, it's not, it's something really benign. I mean, sometimes you have the internet, so. Have you seen the? Like, it was in this show that does now, it's like, but he did like work first and an hour long where he himself on fire. And like, everyone else is like, no. It's like, it's like everyone else is like, and he defends himself too. And so it's like, you know, with his prosecutor and, you know, all these like extra all the, yes.
So in case anyone is interested and wants to stick around, I can show you how to use Octave Online, which if you're these 3D problems, you're going to do a lot of systems of equation solving. And if you don't have that capability on your calculator, you might get to the question. There's a real easy way of doing this with a site called Octave Online. If you could just remember Octave, like musical octave, and then online, just Google that, and you'll get to this site. And for that third 3D problem, right, what you do is in the command line. So actually, I'll just go again to it so you can see what it's like. OctaveOnline.net. It starts off with something that wants you to say how you're using it, but just ignore that. And then the command prompt is down here. This is where you type your commands. And you can just write your whole equation in a form like this. You do a square bracket, and then you take the coefficients of all the terms. Once you have everything in a neat, organized system of equations, then you just put the coefficients in front of it. So who has? So Joel, do you have your equations? So his equations, read off your equation, and I'll just show you how. So the first equation is what's your first equation?
So 600.
Okay, that's the equals though, right? So it has to be like something times F1 plus something times F2 plus something times F3 equals something, right? And you have to put every equation in that form. Yeah, something times F1. What's the something times F1? What is the coefficient of F1 for the first equation? Is it 0?
It's 1.
Is it 1?
It's kind of hard to see because I was writing.
Yeah, so when it's really, yeah, and that's why you got to do this really neatly. You know, accountants, they're really neat people because
let's do my F1.
Engineers are not.
Let's do my F1.
Yeah.
So 3 divided by 5.
Okay.
-3.
But I need the F1 term first, then the F2 term, and then the F3 term. Because that's how you have to do this.
4 divided by 5 F1.
Okay, good.
Minus 12 divided by 25.
And so there's 0 times F2, right?
Mm-hmm.
So then you see what I'm doing? I'm putting 4/5, 0, and then what does that equal? And you can use commas here if you want, but if you just have space, that equals 0. So then we're going to put a 0 on the last number. That's what it equals. Oops, but that's just the first equation. Mm-hmm. Now we go semicolon, it starts another line. Now we did another equation. What's the sum of the FZs?
Mm-hmm.
Something times fx. What's the times fx?
3 divided by 5.
Yeah, I'm sorry, F1, yep. 3 divided by F1. Yeah, you can do it's the same thing.
0 times 2.
Yep, see it.
4 divided by
Okay. So then equals 900.
Yeah.
So it's on the equals goes, you got to do, so this is like something, this plus something, this plus something, this equals 0, or equals 900. Now you got to do the fx equation. Semicolon, go to new line. What is the fx equation? What times f1?
0. I believe
Good.
it's
0,
negative
-1, 9 over 25, -600. That's your whole system of equations. And you can see the terms, make sure they agree with what you think they are. Does that look right? I don't know how to do 25ths in your head, but then you can just say, okay, I need to do RREF, row reduced echelon form. That's basically doing Gauss elimination of your equation. And you got it. Those are the answers, I think. Those are the answers. Mhm. Yeah, and that's why you want to do a tool like this, because if you made a mistake, you go, oh, I didn't get the right answer, and then you look, oh yeah, that was supposed to be 16/25. What you can do is you just hit the up arrow twice, and you go back and change that to something else, right? And you don't have to type it all over again, just do that, and then do up, up, then do the ref again, and it comes up with a new solution with the correction, right? So it's really fast to kind of go through stuff until you get the right. Yeah, you should do that. Yeah. Yep, that's it. Good. I'm glad. Yeah, it's great. Really, people like you who are, ready to go. Gotta find that thing. Thanks.